Hello PCI, we are Taylor Broadbeck, Sam Valmasoy, Mohammed Kambar, and Allison Ebert. We're students from North Carolina State University, and we're excited to share the work we've done for our Big Beam submission. For our design, we decided to use Ultra High Performance Concrete, or UHPC, instead of traditional concrete. If you're not familiar, UHPC is characterized first by its high compressive strength, which is usually above 17.5 KSI. We know, that's a lot. Here's Mohammed not believing his eyes at the cylinder strength. It's also known for its superior tensile capacity, thanks to steel fibers that are well distributed throughout the concrete mixture.
However, this material is, of course, a lot more expensive than traditional concrete, so it was important that our design was as structurally efficient as possible. To come up with our design, we used a mixture of hand calculations and finite element modeling to iterate on optimizing the geometry. This is what our design looks like. The beam is only 10.5 inches tall and is 8 inches wide at the top and 7 inches wide at the bottom. The beam uses 3 9/16 pre-stressing strands in a triangular pattern and actually no shear reinforcement. This is important because we want to minimize the amount of mild steel in this beam so that we don't get any disruption of the flow of the fibers. It also means the geometry of our beam isn't driven by the stirrup dimensions like in a traditional concrete beam, which means our stem can be thinner and our flanges can be narrower. Our predictions for this design are shown here on the screen, where we predicted a cracking load of 20 kips, a failure of 35 kips, and a peak deflection of 4.5 inches.
To get this design produced, we worked with Tyndall Corporation out of their Spartanburg, South Carolina plant. The first step in getting these beams cast was building the formwork. Thanks to the small and custom design of the geometry, the formwork was built on a CNC machine and assembled prior to the arrival of our team in Spartanburg. Seeing the size of the form, it was hard to believe this beam was supposed to sustain an applied load of at least 32 kips, and some of us started getting nervous. Afterwards, we went over to the batching plant to begin mixing our UHPC. Sand had to be added to the mixture, along with about a third of the water that was going to be used. Silica fume was then added by hand and mixed with the sand, followed by the cement and most of the water, minus a few gallons that would be left out to leave room for adjustments. That's when the water reducer and hydration stabilizers were added manually, and a flow measurement was run to make sure we had about an 11-inch flow. Finally, the moment we've all been waiting for, the fibers are added to the mix. All in all, this process took about half an hour, whereas usually a traditional concrete mixture would take the plant less than 5 minutes. This is just because there was a lot of additions that had to be added in by hand, and because these batches are only done about once a year, so the crew was not as experienced with this mix. Also, because the mix was so dry since the water-cement ratio is low, we had to wait a little longer for the mix to become fluid.
Once we had our mix, we went over to our Big Beam's little form and started pouring the concrete in. We also made sure we had enough cylinders and rectangular prisms for our prism tests. We then had our beam show up on the truck. That's our lab zone Dr. Lucier driving the MyJack you see there. After that, we began putting together our test setup. As part of our instrumentation, we use digital image correlation, or DIC, which allows us to view the displacement and strain field throughout loading of the specimen. We'll see more of that when we look at the actual test. Finally, here's our test actually being run. The top two images show two different video angles of the test. The bottom left image shows the principal tensile strains with low strains in purple and high strains in red. The center bottom image shows the principal compressive strains with lower magnitude strains in red and higher magnitude strains in purple. And then finally, the bottom right image shows the load displacement response of the member as the beam is being loaded.
Let's fast forward a little to the cool parts. Here's the beam at the actual cracking load of 20.8 kips. You can see softening of the load displacement plot, as well as some spikes in the principal tensile strains under the second load point on the left.
And then let's fast forward some more to around where we first hit our peak load of 35.4 kips. You can see our beam has deflected substantially. We're seeing large tensile strains shown in red under the second load point, which highlights a wide crack forming.
What's really interesting to see is that if we look at the principal tensile strains, there's really only one crack that is formed at peak load, which we can see from the red color on the plot. This is uncommon for traditional concrete flexural members and is related to the vastly superior bond strength of UHPC.
And then finally, let's fast forward one more time to this point where we can see we've finally started dropping load from our peak, and we're about a displacement of 4 inches when finally wow is right, Dr. Lucier.
The beam ultimately cracked at a load of 20.8 kips. It first peaked at a load of 35.4 kips, at which point the displacement was 2.53 inches. So how does that compare to our predictions? The answer, looking at our pretest prediction, is not bad, especially considering that the beam maintained the peak load through a displacement of 3.2 inches. We predicted a midspan deflection of 4.5 inches at a peak load of 35 kips.
We know what you're probably thinking. I could have done better than that. Well, we wanted to see if that was the case. So we put out a challenge to our lab, the CFL, and that was a blind prediction test. We asked them, given our loading conditions, our beam geometry, and our material properties, what you would predict the ultimate load and the peak displacement. This plot here shows all of our respondents' predictions.
In total, we got 15 responses, 12 from students at the CFL and 3 from CFL professors and staff. Some were calculated, and some were maybe more gut instincts.
Funny enough, we were not the best prediction in the blind prediction contest. But that's okay. That just means we know who to ask for help next year.
This exercise for us highlighted what a great material UHPC is, and how much more structurally efficient we can be if we have, first of all, the confidence to not only try designing with it, but also to wrestle with the logistics of mixing and batching it.
With that being said, we are so thankful to the team at Tyndall that helped us with this project.
Specifically, we'd like to thank Matt Thorne and Tyler Maynor, who supported us along the way with our designs and conceptualization.
We'd also like to thank Taylor Nunemaker, who was instrumental to the mix design and batching of the materials, as well as explaining the process along the way.
Finally, we're also very grateful to our advisor, Dr. Gregory Lucier, for his support throughout this entire project.
Thanks for listening, and
Go
go Pack!